Hello and welcome to our lesson on generating terms in sequences using term-to-term rules. In this lesson, we will be focusing on how to use term-to-term and nth-term rules to generate terms in sequences. We'll begin by reviewing what term-to-term rules are and how they differ from other types of rules you may have seen. Next, we'll go through the process of applying these rules to generate terms in a sequence with step-by-step examples. We will also explore nth-term rules and how to check that a number is in a sequence. We'll work through several cases to solidify your understanding and provide you with practice. With this foundation in place, we are prepared to delve into term-to-term rules. So let's jump right in. Term-to-term rules allow us to generate each term in a sequence by using the previous term or terms. This is different from position-based rules, where you compute the value of a term directly from its position or nth term. Term-to-term rules are very useful when you're dealing with sequences that do not have a clear linear or polynomial relationship. Let's consider some examples to see term-to-term rules in action. First, let's practice generating a simple arithmetic sequence. Suppose we have the following rule. Start with 5 and add 3 to get the next term. The sequence would look like this. First term equals 5. Second term equals 5 plus 3, which is 8. Third term equals 8 plus 3, which is 11. Fourth term is 11 plus 3, which is 14. And so on. Now let's check if a given number is part of a sequence defined by an nth term rule. You need to 1. Write down the expression for the nth term. 2. Set the given number equal to this expression and solve for n. 3. Check if the solution is a whole number. Example: linear sequence with nth term 2n. Is the number 26 part of the sequence represented by nth term 2n? Set 2n equal to 26. Solve for n. N equals 26 divided by 2, which equals 13. Since 13 is a whole number, 26 is indeed a term in this sequence. How do we check if a sequence is an arithmetic sequence? If you only have the sequence values and want to check if the sequence is a linear sequence, determine the differences between each pair of consecutive terms. If the differences are constant, it's a linear sequence. Example: sequence 2, 5, 8, 11. The common difference is 3. It is constant, and hence it is an arithmetic sequence. The nth term will have the form an plus b, where a is the common difference 3. At n equals 1, the term is 2. To find b, we minus the common difference from the first term, so 2 minus 3, which is minus 1. Hence, the nth term expression is 3n minus 1. What do we do if our sequence is non-linear, or in other words, doesn't have a constant difference and so isn't an arithmetic sequence? The next thing we should do is check if it is a quadratic sequence. To do this, we should look for a constant second difference. If there is indeed a constant second difference, then our sequence is quadratic and so the nth term will contain n squared terms. For example, let's observe the sequence 1, 4, 9, 16. First, we find the first differences, which are 3, 5, 7. These are not constant. Next, let's observe the second differences. 2, 2. These are constant. Since the sequence follows n squared, 1 squared, 2 squared, 3 squared, the nth term is n squared. In general, if the sequence has a constant second difference, then the nth term should be in the form an squared plus bn plus c. Now let's try finding the value of a term in the sequence from the nth term rule. Once the nth term rule is known, you can generate any term by substituting the position number into the rule. Suppose the nth term expression is 3n minus 1. To find the fourth term, do 3 times 4 take away 1. If we solve this equation, we find that our fourth term is 11. Sometimes sequences may not fit easily into nth term rules, especially in more complex scenarios. In these scenarios, you should try to find the term-to-term rule for the sequence. Some things to look out for when you are looking for a term-to-term rule are relationships between adjacent terms and common differences or ratios. After spotting a pattern, you should then infer the rule. For example, if you have the sequence 2, 4, 8, 16. Here you should notice that each term is twice the previous one, and so mathematically you can write the term-to-term rule a times n plus 1 equals 2 times a multiplied by n. Let's now practice identifying and generating terms using term-to-term rules through another exercise. Alright, let's imagine you're stacking building blocks. You start with one block, then add 2 blocks to it, then 3, then 4, and so on. This is a sequence. 1, 3, 6, 10. What would be the 10th term? It may seem difficult at first, but look for patterns in the differences to work out our term-to-term rule. Our term-to-term rule is add the next consecutive number to the current total. So let's begin this process. Our first stack was 1 block. For the second stack, we added 2 blocks. So 1 plus 2, which makes 3. For the third stack, we added an extra 3 blocks to our second stack, so 3 plus 3 giving us 6. Then, for our fourth stack, you guessed it, we added 4 blocks to our third stack, so 6 plus 4 to get 10. As per our rule, we are adding the next consecutive number at each step. To continue generating the sequence, we'll just keep following our rule. For our fifth stack, we'll add 5 blocks to the fourth stack, giving us a total of 15 blocks. To get to our 10th term, we'd keep doing this until our 10th stack, where we would add 10 blocks to our 9th stack. Our 9th stack includes 45 blocks, so when we add 10, we get the answer to our problem of 55 blocks. This is termed as a triangular sequence, and it's an application of term-to-term rules. What's particularly neat about this is that we didn't need to start from the beginning each time. We could start from any term and apply the rule to get the next term. This example gives you a sense of how term-to-term rules can turn complex number patterns into straightforward processes. In today's lesson, we explored the process of generating terms in sequences using term-to-term rules. We started by defining term-to-term rules and distinguishing them from position-based rules. Through examples like a simple arithmetic sequence, we demonstrated how to apply these rules to generate subsequent terms. We also discussed how to check if a given number is part of a sequence using an nth term rule and worked on deriving nth term rules from given sequences. Additionally, we covered how to identify term-to-term rules in more complex sequences. Finally, we practiced generating terms using both nth term and term-to-term rules to solidify our understanding. Watch the rest of the GCSE Maths course at Sophos Education.